Okay, we're going to look at 10.7 first, and there's a good deal in this, a lot of different parts to it. You've seen some of this before, so it's not brand new, but it's good to look at some of the details in it, because it is a part of integrated 3 standards. And then after that, we're going to look into 11.1, maybe 11.2. I'm hoping to get through those 2 sections. So we basically get a little bit of beginning calculus for you today. I get the easy parts of calculus this month. You get some harder things with Mr. Green next year in AP Calc, or if you do a different calc in a different place. Whatever it is, you still, like everything else in math, if you learn the basic things really well, it makes the things that are later come a lot easier. So learning limits and then derivatives will, if you get really comfortable with what they're about, then doing calculus will all be a good deal easier. All the things that come after it. But first we're going to look at empirical probability and theoretical probability. And let's do a couple of examples. So first, this one is what's considered experimental. Not like you're making an experiment or it's like uncertain what it's going to be. It's more like already observed, actually observed occurrences. Observed, that's supposed to be occurrences. So another way to think of it is that this actually happened. Something that actually happened and the percentage is here. So I'm going to take as an example the month 8 test. I like my grade program because it actually will give me some statistics with it. So I found some statistics. So there were 92 students who took it, and I'm not talking, of course, just this class. It's never been that much. But all of my classes together were the ones who took that test. There were 92 students. And the number of people who earned an A on the test were 33, and the number of people who earned a B were 16. And the number of people who earned a C were 21. The number of people who earned a D were 12. And sadly, I had 14 people who did not prepare well enough for their tests. So that's the way I think about it. When somebody does poorly, like a D or an F, or even in some cases a C, it's because they didn't prepare quite as well as maybe they should have, or they didn't come to get help. Anyway, enough about that. The idea here is that in an actually observed incident where you have exact numbers, what you're looking for is if you randomly picked one of those 92 people, what would the chance be that they fell into one of these categories? And that's just a simple fraction. So 33 over 92, I figured that before. Oh, it comes out to a fraction of 0.35869. Well, you have to make this, or you have to be able to make this a percentage. So you can't round it to 0.4, because that's way off anyway. Your best bet is to think about it going 2 places, then go 1 more, and think, okay, if I round that 6 would make it a 9. So think of that as 0.359. And then you can make that a percent to make that 35.9%. That one's so close to 36 that it's very reasonable to think of it as 36%. So there's a 36% chance that if I randomly pick someone out of this room, that they are one of the 33 people who got an A out of the 92. So 36%. Okay. Yes?
I don't remember, so it goes up to 96.
What time's up? 96?
Yeah, all the numbers.
Oh. Thank you for checking that. 10, 13, 15, 16, 17, oh, 10. Yeah, you're right, I'm off.
Yeah, but it does come.
Yeah, so when I came up with this numbers, I'm thinking of the chart that I used to get it. I did not verify it and see why. So I'm going to have to go back later and figure out why, because it's clearly not that enough to figure out why it said that. And I'm not sure. So I'll go and look later on. For now, for the purpose of this, let's pretend it's 92. Okay? And I'm only going to do a couple of these, because here's the next place to go with it. Let's say it's 12, and let's say I say the people who really have to retake the test. Now, in reality, I think even people that C's, it would be worth it for them to retake it. But the people who need to retake that test comes to a total of 26. And if it really were 92 that was the total, I just do 26 over 92 and calculate that, and that one I didn't do before, so let's do it now. 26 divided by the 92. Oops, I'm in the wrong spot. 26 divided by 92 gives me a 0.2826, so that's 28.26 or 28.3%. I could just say 28%, but yeah, it's reasonable there unless you're told to go to a certain place, you do what's reasonable. So even 28% would be a reasonable amount. So a little more than a quarter of the students should be retaking the test. Now, once I fix that, I'll get the exact numbers, but you get the idea where it should be there. I'm going to have to go in, because that's a problem with the grade program that I'm using, because I got these directly out of it at the same time, so I don't know why it's not matching. I will figure that out later. Okay. Now, back to, that's empirical probability. The idea here is there are things actually done, and you're seeing what the chance is, what the probability is that someone is in one of those categories already. We're going to look at next, the second part of this section is theoretical probability. Think of this as it hasn't happened yet. And if it were to happen, what's the chance that maybe that you will get that result? We usually do theoretical probability just because of ease with it. We do problems involving dice, involving cards, and involving the lottery. So you'll see some problems from me on those three things because they're very common to the point where you will usually see probability questions on state tests, on the SATs, on other things like that involving these kinds of things. Sometimes you'll see them with marbles in a bag. I think you've seen that in past in my classes too. And those are good, but there's, in a way, those are a little limited, which is why you don't see them as much now. You have a lot more possibilities to play with these things. Okay. It's like, and for the lottery, it's like, I am not a believer, a firm believer in using the lottery, and you'll see why with the percentages, but this is the one good reason to have a lottery, so we get good math problems out of it. So we'll get a couple in a few minutes. So let's start. One of the few things I can draw is a cube, which is perfect if I'm going to talk about probability dice. Ooh, let's see, am I really able to do this one? Yeah, I guess I come this way and that way. Okay, so there, I have done a die. One dot, two dots, three dots. And notice I'm not putting the 4, 5, and 6 ones. I didn't choose those sides, so this is a lot easier for me. So there's a nice little picture to go along with what we do. So if you roll a die, you have a possibility of getting a 1, or a 2, or a 3, or a 4, or a 5, or a 6. This is called the sample space. The possibilities that you could get is the sample space. That's just vocabulary, but you see it often enough, you should just be comfortable with using that. So let's think, what is the probability of each one of those things? The probability of getting 1, if you roll it once, well, unless it's a weighted die, which you hopefully don't have, but a real one, you have a 1 chance out of 6, and you have a 1 chance out of 6, 1 chance out of 6. All of them are the same. Now, if you're playing certain games with dice, you don't really believe that because it never seems to come up with the numbers you want it to. But in reality, you have an even chance for each one of those. So now, what we're going to do, immediately start with the right notation here. P1, that kind of math notation means the probability that you will get this result. Well, the probability that you will get a 1 is simply 1/6. The probability that you will get an even number, so notice what I'm doing here is I'm now sort of changing this. Probability to get an even number will be this one here, and this one here, and this one here. So you have a 1/6 plus another 1/6 plus another 1/6, 3/6, which is never acceptable. That means there's a 1/2. You have a 1 out of 2 chance of rolling an even number, which makes sense. You know die, you can see how this kind of thing works. Okay? By the way, if we had done this as experimental probability, would have rolled about a die like 50 or 100 times and seen how many times each one showed up, and then done the percentages based on those results. But we're not doing that. We're doing it based on what should come up, what the theory says, what a normal average, like what it should be. It seldom is exactly that way, you know, from games, but okay. Let's do another one. Greater than 1. You notice I can play with this. There's a limitation to this. I can do a lot more with cards, and we'll do that in a few moments on it. But greater than 1 means all of these. So it means there's 5 possibilities, so you have a 5 out of 6 chance of rolling something that's greater than 1. Notice the notation here, the probability of getting that result, because you're going to use that. If you haven't already done this section, if you have, you should be used to it already. If you haven't, then you want to get used to it. Okay, now here's more part 2. I'm going to call this B. B. Now here, let's make this a little more challenging, or a little more like, let's do more with it, by using 2 dice. Instead of 1 die, we'll use 2 dice. And the sample space for that is the combination of, if you roll one and you roll another, it's the combination of both of those. And that's where you can use a chart. What I want you to do is draw for me a little table and do 2, 1, I do, oops, I don't have to do, yeah, I guess I'm going to do lines right now. 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. So this kind of chart doesn't take that much work to do. And if I were to ask a question on a test that involved 2 dice, it may or may not be worth your while to make this, but it's not that hard to make. Because 1 plus 1, you get a 2 here. 2 plus 1 is a 3. 3 plus 1 is a 4. Well, then it becomes really easy to fill out. 2 plus 1 is 3, and then 4, 5, 6, 7, 8. So take a moment, please, to actually do these. If you don't really care about making it perfectly neat, then this is really fast. If you're obsessive with having it really, really neat, it'll look great, but it will take more time. So depending upon how much time you have, you don't have to be really neat. Especially since we're going to draw it in a couple minutes anyway. And then we'll use it to figure out some probabilities. For instance, the probability that you will roll a 7 when you roll 2 die. Now, that's where the table can start coming in very handy, because you can pretty easily tell you have this row of 7s and they're the only ones. So you have 1, 2, 3, 4, 5, 6. So that's 6 good possible outcomes out of 6 times 6, out of 36 total in the sample space. So the way to think about this is it's a pretty easy number to work with, but really what's important is the concept that these are correct or wanted outcomes. I guess you'd say successful outcomes. Successful outcomes. And we're dividing it by the total outcomes of the sample space. Total outcomes, which is the sample space. Of course, we have to reduce it, but where those numbers come from is what you actually can get, or what you see as possible, divided by the total. So that means you have a 1 in 6 chance of getting a 7. So every 6 times you roll, you ought to get a 7 once. Never seems to happen that way, but that is what's the idea. If you were to roll 2 die 1 million times, the chances are that it would come very close to this kind of result, that you would get that percentage, which would be, this one's what, 1/6 is 18, about 18%, I believe. And you would get it just about 18% of the time if you did this like 1 million times. If you only do it if you do it 36 times, chances are you'd be somewhat off. But if you did do it a million times, you get closer and closer probably. Okay? So, now let's do the probability of, oh, I like that. Let's do greater than 5. Greater than 5. So I can do this with things. We look at the 5s, and we see, okay, we have 5 6s, 6 7s, 5 8s, 4 9s, 3, you get the idea. The 6s and the 8s make 10, so that's 16, 17, 18, 19, 20, 23, 24, 25, I believe that's 26. Someone can contradict me if you think I'm wrong, but I'm pretty sure I got 26 and 36. So it's 26 possibilities that would be correct here, because it would be all of these here. I'll draw in mine. You don't have to draw in yours, but I did for the fun of it here now. So now I'm going to get 26 over 36, and what I can do is I can start reducing that as 13 over 18. Yeah, 18, and that's about as far as I can go. Now I can say it's a chance of 13 out of 18 times, but this is also where the percentage comes in very handy. Because the probability can be done as a fraction, or it can be done as a decimal, 13 divided by 18. So that would be 0.722, approximately, because it rounds. Usually it's done at least 2 decimal places. It doesn't have to be done 3. I like to do it to round it, but it doesn't have to be. And then that means that's approximately 72%. These two are more common. You can do this in certain cases, like with the lottery, that becomes really helpful and useful. But these two are very common for probability. Because probability is always between 0 and 1 for decimals and 0 and 100%, because you're not going to have a probability of more than 100%. 100% is absolutely going to happen. You can't really go beyond that. 0% is there's no chance. You can't really go below that. And there's time to see otherwise. Okay. So this is an example using dice and just simply the idea of outcomes and sample space. Now let's take a look at this with a similar type of thing with playing cards. And in particular, let's see, that's 2, I'm calling this parts. Oh, this is still part 2 actually. But it's sort of like the third thing in part 2. Okay? And it's probability, and we're going to use standard playing cards. So some people are very comfortable with these with various games they've played, but let me go over the basics. Because if you're someone in a family where that's not something you've done much, playing cards, then you still need to know about them because of the chance and probability questions. You get higher up in math, it becomes a common thing. You don't have to play them in order to know about them. So basic things is that there's 4 suits, 52 cards total, and there's 4 suits, 2 red and 2 black, and so they cut them exactly in half. And then in each suit, there's an ace, a king, queen, a jack, and then 10, 9, 8, 7, 6, 5, 4, 3, and 2. There's no 1 because in some games the ace counts as 1 and others it counts as 10 or 15, usually 15. But there's no 1 card that's a 1 since that sometimes is used for it. And the other thing to be aware of, I also need to tell you because of some problems, is that the red ones are the hearts and diamonds, and the black ones are the clubs and spades. Because if it was asked in a question of what's the probability of getting the king of hearts or the 8 of spades, then you need to know that one's red and one's black and what the result is, or red ones. You'll see when we get to some of those problems. And the other thing is that these are called face cards. Sometimes they're just called picture cards, but usually face cards is the more common term. And because the king, queen, and jack have faces on them. That sort of makes sense. So here's what we're going to do. There's 52 cards total, so that makes it your sample space. So let's do a probability. Probability that you were to get an ace if you were just randomly to pick a card. Well, that's where you have to determine what that means. There's an ace in every one of the suits. That means there's one hearts ace, one diamonds ace, one club skate. You get the idea, there's 4 of them. So that means there's 4 out of the total of 52, which means it's 1 out of 13. Okay? And then this is where you could make that a percent. It would come to approximately 7.7% or 0.077 or 0.08, but 7.7% is like a good number. So 7.7% of the time you would pull out an ace. That's supposedly what this would mean. Well, now let's do it, it's just any one number, and that would have been true if I'd said king or 10 or 5, because there's 4 of each of them. Right, so it's an easy question. Well, what about instead that we do probability of a face card? Well, it's the same concept. It's out of 52. Figure out how many face cards, and you've got 3, 6, 12. We've got 12 of them. There's 3 in each of the 4 suits. 3 times 4 is 12. Counting principle, fundamental counting principle for that one. And then that reduces to 6 over 26, and that reduces to 3 over 13. All right. And I didn't quite do the decimal, but that would be 3 times that, so it would be 21, 23. It should be about 23%. It should be. So I can guess that. Let's see. 23%. 3 divided by 13. Yep, 23.07 or approximately 23%. So that means the chance of getting a face card is almost 1 out of 4. It's almost a quarter of the time. I hadn't actually thought about that. I play some games with cards, but not a lot much, so I haven't been thinking about it getting used to it. And part of that's because that in this set of cards, let's say there's 13 of them, so 3 out of 12 would have been 1/4. Well, this is 3 out of 13, so it's slightly less than 1/4, and that's what 23% is, so it makes sense. Okay, now, we're going to use these again in another way in a few moments, the probability of not getting something, but first I want to go into a different type of problem, and that's a lottery problem. Now we're going to part 3. Now, a lottery problem is actually a theoretical problem because even though they base it on how many people are buying tickets, it's not till after the lottery that you see how many winning tickets there were, how many second place or third place or for each of the prizes. You don't know that at first. So what you have to base it on is theoretically what would happen before there's picked. There's a number of ways that the lotteries, I think it's like 22 or 23 states in the U.S. have a lottery, and the ones that do it, there's different ways, but the most common way is that they'll have 55 numbers, and you have to pick 6 matching ones. So once or twice a week, they will reach into a bin with the ball popping around. You can see it on TV once in a while. The California one does this. And they'll pull out one, and they'll pull out another, and it's supposed to be as random as possible. They try to do everything so there's no accusations of being unfair, because there's millions of dollars at stake. But if you can get 6 matching ones, well, what we're going to do here is see that it's 55 total numbers, and 6 of them are being taken. 6 of them being taken at a time. The order of these does not matter. If you have the numbers 1, 7, 14, 21, and so on, it doesn't matter whether the 1 is picked first or the 14 is picked first, as long as the final 6 numbers are the numbers that somebody has on their card. Okay? So what that does is that makes it a combination. Now I'm going to set this up from just like the permutation combination thing. It's a combination of 55 things, but 6 of them being taken at a time. That notation you've seen, you're used to it. We're going to use that now to find the probability of winning this. Okay? First, let's find how many possible ways that you could get the 6 tickets. How many possible ways? Okay, so that is 55 factorial over 55 minus 6 factorial over 6 factorial. Got a lot of work to do with that. Did I show you how to put that in the calculator? Mm-hmm. Yep, okay, good. So if you do that and put it in the calculator, I'll just tell you right now, I get 28,989, 675. So that means that there are this many ways that 6 numbers can be pulled out. One of those ways is 1, 2, 3, 4, 5, 6. Another one is 2, 3, 4, 5, 6, 7. Another one is 1, 3, 5, 7, 9, 11. And you can keep on going, keep on going. The chance that the one winning one, the chance you have of getting the winning one, the probability of the winner is one of those, because of all the possible 6s, only one of them wins. It's 1 over the total sample space of 28,989,675. If you put that into a decimal, it's 1, 2, 3, 4, 5, 6, 7 zeros before you get to a significant number. 0, 0, 0, 0, 0, 0, 0, 3, 4, 5. You can't even make it a decimal because you can't move the decimal, you move it only twice and you're still far away from calling it decimal. So it's better in this case to say that the chance of picking the probability of the winner is 1 in 28,989, 28,989,675 possibilities. So you have a 1 in about 29 million chance of getting it. So the term some of us like to say is that people who play the lottery, or that the lottery is actually a tax. It's a tax put out by the government to tax those people who don't understand math. Because if you understand math, you're probably not going to put $10 towards tickets every Saturday or Wednesday or things like that, because the chance of you winning, even if you got 10 tickets, you have 10 chances out of 29 million possibilities. So I sort of like that phrase. It's a tax on those people who don't know their math skills. You guys know your math skills. So you're welcome to play the lottery once you're old enough, but I don't recommend it. Here's why. Anyway, it makes for a good math problem because we're talking about how to figure out the sample space, and then the probability, which you could play with. You could even say, what's the probability if you had, say, 100 tickets? Because there are some groups of people where they work somewhere and they'll all pitch in some money and they'll get a block of 100 tickets. So if you put 100 here, well, then you take a couple of these away, so you're actually down to, what, 2 million? Let's see, 1, 2, 3. Yeah, you have a 289,000%, 1 out of 289, 290, 1 out of 300,000 chance. That's a lot better than 29 million. Still don't think I want to put my money towards it. Anyway, you play with things like that. Now, each of these things, whether we're talking dice, or we're talking cards, with the sample space, you have to understand a little bit of details in that, or with the lottery, they're all done the same way for finding the probability of what you want. You do the number that would be correct for what you want divided by the sample space. Now, fourth thing is, what if it's what we don't want? Okay, fourth thing. The probability of not getting the result. So what's the probability of not getting it? Well, let's come back to the original dice problem. I'll go to this dice problem. So we figured out that the probability of getting a 7 is 1 out of 6. So probability of a 7 is 1 out of 6. So that's when there's 2 dice. The probability of not getting a 7, not 7, the way you calculate is 1 minus 1/6, because 1 is the total thing, as if everything was 100% chance. You subtract from it the chance of getting a 7, and everything that's left over is not a 7. So here we'd have to make it 6 over 6 minus 1 over 6, so it's a 5 over 6 chance. So the probability of not getting a 7 is 5 over 6, which makes complete sense. 1 over 6 plus 5 over 6 adds up to 1. So the math in this is not all that hard, except for making it making the fraction here. So let's then think of it with cards. The probability of not a face card. The probability you get a number card, and the ace counts as a number card, so it's just a face card. So remember that the probability of getting a face card was 3 over 13. So that means this is going to be 1 minus 3 over 13. That's 13 over 13, so that means that the answer is 10 over 13, which I can also make the decimals too. The other one was, oh, I never figured it out. Oh, I did. It was like 3 times 1. It was, oh, I remember now. That's why. Well, it was like 23%. That's right. It was 23%, so this would be 77%. Lottery. Probability of not winning the lottery. That's going to be 1 minus, oh, and now I'll get that nice big number out. One over 28,989,675 is well, it is equal to 28,989,674 over 289,89675. Oh, that's a pain to write. Well, in decimal form, that's 0.99, I think it's 7 nines ago, 3, 4, 5, 6, 7 nines before I get to a different significant number. And if I move the decimal over twice, then it's 99.9%, 99.99%. You can go as far as you want. So the chance of your not winning in the lottery is 99.99% chance. That one works for me too. And you can see how...
If you round it, it's 100.
Yeah, it's so close, it's almost like the limit of it, which is where we're going to go in a moment. A couple more. So recognizing not getting the result is just adding up to 1 or taking from 1, and that's a pretty easy one too to understand. Okay. There's still more in this section. Let me get the next part. Uh-oh, I have my notes. Here they are, okay. So this is the 5th part. 2 mutual excuses. Okay. 2 mutually exclusive events. So let me put it this way. Either of 2 mutually exclusive events. So let's go back to cards. And let's say we're going to pick one card, and we want it to be an ace or a king. We can't have it be and a king because we're only picking one card, so you can't have both things at once. So it's really, you want to pick one card and you'll be happy if it's an ace or if it's a king. So 2 things will make you happy. Right? So the probability of an ace is 4 out of 52. The probability of getting a king is the same 4 out of 52. If it doesn't matter to you which one, and you could be happy with either of them, then that means you're adding these probabilities to get the total probability of the chance of what you want. So that means it would be 8 over 52. Well, it was 1 over 13 and 1 over 13. This is actually 2 over 13. So I'm just going to do 1 over 13 plus 1 over 13. So that is the probability that, that we would get an ace or a king. So So think about how that works. It's the probability of one, just simply plus the probability of the other, and it makes sense because you're happy with either one of them. So this would be good, and this would be good, so you'd add them together for the total amount. Now, here's another one. Pick a face card or a 5. Just like this one, go ahead and figure that out yourself right now. Remember what it means of how many face cards there are. And then figure out what's the probability of getting a face card or getting a 5. Doesn't matter which suit here. Just a matter of those. So remember what it is to get those. So figure out what those are and add them up. I'm just going to make the 5 instead of 4 out of 52, they reduced 1 over 13. Because if you think about it the same way, for the face card, there were 12 out of 52, which is the same as 3 over 13 for each. So that means the chance here is a 4 out of 13 probability. That's what you should have been able to come up with. If you do that, you should have the basic idea here of how to do them. Now, here's another one to practice, this time with the dice. Can't get the word practice down here. So what's the probability of rolling a, 2 dice? So I want to know what the probability is of rolling a 1 or a 2 or a 3. Just the low numbers. What's the probability of running each? So go ahead and figure that out, please. P1 and P2. Figure out the probability of each of those. And then, of course, add them up. Tiny little bit of a trick in there. But if you think about what probability means, you can realize that in the case of 1, well, there is no 1. If you roll 2 die, it's not possible to get this result. And you can calculate that as just equal to 0. So since it's not possible to get that, that's 0 chances out of 36. There's only 1 2 and there's 2 3s, so it's a 1 out of 12 chance that you would get a...
You can't get a 1, you don't have a 0.
Yeah, so this is all out. Well, it's not that you don't have a 0, it's that, yeah, you're right, on the die you don't. You have, so that's why it's a 0 out of 36 chance, you don't have to add it. But the chance of getting a 2, there is 1 possible way of getting a 2, and there's 2 possible ways of getting a 3, so those you can do. But you see this once in a while. Sometimes thrown in, you think of it as a trick, but part of it is to see if you understand that concept, that it's based on reality, that that's not something that's possible to do. Now, these types of problems are all ones where they're separate from each other. You get this one, or you get this one, either of those will make you happy. Same thing's going to be true with a variation for the next thing we do. This was 2 mutually exclusive events, but here are 2 that are not mutually exclusive. Okay, so call this the 6th part of this. The one is either of 2 events not mutually exclusive. So, pick 1 card, and we're going to say it's an ace or a red card. So the probability of an ace, the probability of a red card, well, for an ace, there was 4 chances out of 52. For a red card, it's exactly half of them, 6 out of 52, whoops, transpose those. Problem we have is that there are 2 aces that are red. So what's happening here is we can get 4 aces here, but 2 of those aces are repeated over here. So that would give us a skewed result. We can add these together, but it's not going to be correct because 2 of these are actually here as well. So what you have to do is you have to account for that and subtract 2 of them that are in both categories. You only need them in one. So you put them in the both and then you subtract them out of either one of the categories. So this is where it starts getting just slightly tricky, and you have to think, well, what are the things where, how many are there that are in each set that's the same, and then subtract those. So that's going to be 24 and 4, that's going to be 28 out of 52, which is 7 over 13. So it's 7 chances out of 13 that you'll get an ace or a red card, which is just a tiny bit over 50%, which makes sense. All the red cards and 2 more makes just slightly more than half of them. Now, what about the probability of a face card plus the probability that it'll be a black card? I've been dealing with the red ones there, so let's do that. Go ahead and figure that out. You're going to figure out how many face cards, how many black cards, and then see what you need to subtract. How many are there that's in both of them, that's in both categories? Go ahead and do that, please. Well, I do it up here. If you got it done, take a look up here to see that if you identify that there's 12 face cards, and of course black is half of one, it's 6 of them, because there's 3 in clubs and 3 in spades, 3 in both of the black ones. So you're subtracting 6 this time. And that gives you 8 out of 13, which is a little bit more than half, a little bit more than the last one as well. One last probability problem. All of these that we did so far is where you're picking one thing. So you have one good result here. Well, now what we're going to look at is where you do something 2 times. So let's do that with a dice problem. 1, 1, 2 independent events. There's also 2 dependent events, but it's not in this section, and I think this section's big enough, so I won't add to it. So 2 independent events. Roll a die, then roll again. Okay? So this is not where we're rolling 2 of them and getting like 6 and 5 makes an 11. It's rather you're rolling 1. So you get one thing, and then you roll again to see what you get that time. So what's the probability that we would get a 6? And then, if we rolled it again, what's the probability that we'd go on the other side and get a 1? And notice I put it as multiplying. Because what here is, once you roll a 6, you have a 1 in a 6 chance that you get that. When you roll a 1, you have a 1 in a 6 chance that you get that. The chance that you roll this and then that you do roll that again after that becomes a very small amount. Out of every 36 times that you roll a die and then another die, the chance that you get a 6 first and a 1 second is 1 chance out of 36. And it sort of makes sense if you think about that. The first time that you roll it, you could have rolled a 5, in which case the next time you might roll a 1, but it's not a correct one now. You could have rolled a 4 the first time, and then the next time you roll, you might have gotten a 1, but it's not good. So you have to roll a 6 first in order for this one to even come into play. And to roll that one, you only have a 1 in 6 chance, so you have to multiply that times whatever this chance is. And that's the basic concept here. This becomes a really easy one. Think about it now if you said, what's the probability if I roll an even one, and then the probability that I roll one that is greater than 4. So the probability of an even roll when you do that is 1/2. The probability that it's greater than 4 means a 5 or a 6, and either one, which means it's 1/6 plus 1/6 or 1/3. You just multiply that, and it becomes, there's actually a 1 in 6 chance, because you have a chance of, first a 50% chance that you roll an even one, and then when you roll the next one, it's only a 1/3 chance. That reduces it down to 1/6. Still better than 1 out of 36. But you can see how that combination thing is working.